Hi, welcome to another lecture on Calculus 2. Today we are going to talk about polar coordinates. The issue is how do we give location of a point on a plane or a page. Up until now, probably you have only used the Cartesian coordinates. So this is pair of x and y that you are familiar with from pre-calculus and calculus 1. We want to take a look at polar grid or polar coordinates, which are characterized by r and theta. R is distance from the origin, and theta is the angle we make with the x-axis. Polar coordinates are suitable for situations where you have a rotational motion in your mind. So, for example, if you have planets going around the sun, or perhaps a piece of engine rotating around the main shaft and situations like that, then polar coordinates are the suitable choices. So let's go ahead and just practice this concept. So polar coordinates, just like Cartesian, the pair of numbers. The first one is the distance and second one is the angle. Let's go ahead and practice that concept and see what is meant by it. Suppose we want to plot 2 and say pi over 4. What does that mean? Well, we start with our standard coordinate system. So we do still have the x-axis. X-axis sometimes is referred to as the polar axis now. So this polar axis is same as x-axis. So we have our units here, 1 and then 2 and so on. The angle, now once I specify the radius 2, I go ahead and consider a circle of radius 2 here. So let's suppose we have something like this. So this is r is equal to 2. On this circle, I go, if this is positive, I go in a counterclockwise direction by an angle indicated by this. And pretty much all the time we are going to use radians. So pi over 4, that would be the same as 45 degrees. So I will travel 45 degrees or pi over 4 radians. And then this will be the point that is going to be labeled with r equal to 2 and theta equal to pi over 4. Well, what if I had 2 and pi half? Well, I will arrive at this point. How about 2 and 3 pi over 4? Of course, I'll be here. And 2 and pi. By now, I have reached this point, opposite of our starting point here. How about 2 and 3 pi over 2? Remember, we are going counterclockwise direction, so 3 pi over 2 will bring us to this location. You might think, well, there's an easier way of coming here, which is go in this direction. Well, if you do go in that direction, the angles are going to be counted negative. So clockwise associates with negative angles, and counterclockwise associates with angles that are measured in the positive numbers. So one of the problems that we are going to encounter in polar coordinates is that same point can have many different representations. So one of these representations is caused by the fact that you're going in the positive direction, the other one in negative direction. They are coming to the same point. We did not have this issue with the Cartesian coordinate system. There was no way of changing either x and y and then arriving at the same destination. But with polar coordinate, this is quite common and actually is going to create a bit of a challenge for us. As if that wasn't enough, once I, let's see, sorry. So So if I travel angle of 3 pi over 2 and arrive at this location, if I wish, I can actually continue, go around the circle and come back to this location a second time. So that's going to be, each time we go around the circle is going to be angle of 2 pi. So if I have come to 3 pi over 2 and add the 2 pi to it and take a common denominator, so this is 3 pi and the other one is 4 pi, so 7 pi over 2. So 2 and 7 pi over 2 also represents this this location. And similarly, if I take this trip that I took in a negative direction, I go around and come back to this location, I will have minus pi over 2, and then I have gone in a negative direction with minus 2 pi, and now I have minus pi and then minus 4 pi. That makes it minus 5 pi over 2. That is also representing the same location. So we see one of the first challenges here that we have a doubly infinite list of coordinates, all of which represent the same page, same point on the page. So if I have r and theta, I can say that this is representing the same point that this one does. So I have theta plus 2 pi n. When I go through positive ends, I make this list. If I go through negative ends, so if I take this thing and subtract 2 pi from it, I get the other one. And these are all representing the same point. Now, to add to this complication, we are also going to allow the possibility that r will be negative. So we'll have an issue of what is meant by a negative r. What is meant by that? To understand what the negative r means, again, consider your x-axis. Fix your mind on a certain theta. Let's just say theta equal to pi over 4. So I take this axis and turn it by pi over 4. So that's my theta. Now I will have an axis here. Well, that axis has a positive side and negative side. This is a positive side of it, this is a negative side of it. So if I want to go to point r equal to 2, that would be r equal to 2. But I also could go to the other side and make sense of what would be r equal to minus 2. So during the rotation, if you think about your axis being rotated, then you can think about all the positive numbers here lining up in your new axis, and all the negative numbers that you had on the other side of the original axis are still present on this new axis. Let's go ahead and practice this one. Suppose I ask you to graph minus 2 and pi over 4. Well, this is what we actually did. So I go by my angle. I have a new axis. On that axis, I locate the location minus 2. So that would be that location. Let's try another one. Suppose I talk about location minus 3 and minus pi 6. Where is that? So we take our x-axis, rotate it by minus pi 6. So minus pi 6, you know, remember is just 30 degrees. Minus means go in the clockwise direction, and here, so here is our theta is minus pi 6. The axis is going to inherit this direction from your x-axis. You rotate that and then you, excuse me, pi 6. You get that new axis. On that new axis, you ask yourself, where is minus 3? So that's minus 3 here, so that's going to be this one. So let's see what happens. So suppose, once again, uh, suppose you are at the location r and theta. Well, we said you can go around this positive or negative and then make r and theta a plus 2n pi. 2n pi just indicates how much you're willing to rotate and come back to this location. So this problem is quite familiar to you if you are watching any kind of sports that happen on a track, like cars, horses, people. When people go on a track, it becomes a bit hard to figure out who's first and who's second, because it could be that a fast person, so suppose this is a slow person and this is a fast person. How can a fast person be before the slow person? Because the fast person has gone around the circle several times and now it appears to be behind S, but in reality he is ahead. So that's always a confusing thing that when you're watching the car racing and such, it's hard to tell who has gone how many laps, and skating and running and so on. All of them have this issue. Uh, so uh, 2n pi indicates how many times we have gone around the circle in addition to whatever the theta was. Now, to add more complication to this thing, we can think about an angle of, so I can have an angle of, come to this side where I'll have the angle of pi plus theta. I've got an additional pi, and then if that is my the angle of my axis, then I can choose a negative r and arrive at the same destination. Okay, so I am going to rotate by pi plus theta, and on that axis back up to this location. So I'll have pi plus theta, and then I back up to this to arrive at minus r. And then, of course, I can still rotate as many times as I want in any direction I want, and that's going to be an additional 2n pi. So to summarize, it becomes minus r, and angle is theta. 2n pi and a pi becomes 2n plus 1 pi. So the way you remember this, here it's an even multiple of pi, and this is an odd multiple of a pi. This is an even multiple of pi, indicating as to uh, how to arrive at this point. So this is what we refer to by having a doubly infinite list of coordinates just to represent a point. So r and theta plus 2n pi, and minus r and theta plus 2n plus 1 pi. They all represent the same point. So you need to practice this negative r to make sure that is a comfortable concept for you. Is that the end of complications here? Well, unfortunately, no. There we have one more thing to watch out for, is the following. What if I want to refer to the origin itself? So the question is how to represent the origin. In Cartesian, it was very straightforward, just 0, 0, then you are at the origin. How about here? Well, obviously, you're not away from the origin, so r is 0. No issue with that. R is 0. How about theta? At what angle have I moved to arrive at this point? Well, you can choose any angle. It would not make any difference. You're not moving away from the origin, So a theta could be undefined or any number brings us to the origin. So if I say plot 0 and pi third, well, distance r is 0, I'll be here. How about pi third? Well, it's actually irrelevant. And how about 0 and pi over 2? Well, that's the same point. How about 0 and 0? That is the same point. How about 0 and 100 pi? That's all same thing. These are all representing the same point. So that is an issue to watch out for when you're doing graphing and intersection and such. Some puzzling things come up, and it's good to have a heads up ahead of time before we get there. Okay, after all of this um, talk about the exceptions and some challenges, let's go after some straightforward relationship between what we are getting ourselves into and the old stuff that we had. So when we are having Cartesian versus polar, it's like having two languages, and we want to be able to translate between them. We want to be able to go from Cartesian to polar, from polar back to the Cartesian, because sometimes we change our mind about some equation. We want to go to the old format, or we have an equation in the old format. We want to cast it into the new format. So just like the problems that you have with various computer files that you want to change a format, here is the same thing. So what we want to do is the next topic is relationship between polar and Cartesian. You remember, of course, Cartesian is named after Descartes, the French philosopher who made this popular. Well, let's go to standard setting. So we have our x and y axis. We have some point here. That point is of distance r and has some angle theta. And this is the y coordinate of this point, and this is the x coordinate of this point. So what we do is to just focus on this triangle and write relationships we learned from trigonometry. So in that context, this is adjacent, that's the opposite, that's hypotenuse, that's the angle that you're dealing with. So what's the connection between x, adjacent, hypotenuse, and the angle? Well, perhaps you want to review cosine was a ratio of adjacent to the hypotenuse, from which you get x is equal to r cosine theta by cross multiplying. Similarly, in trigonometry, you define sine as a ratio of opposite to hypotenuse, which tells you y is equal to r sine theta. So these are the relationships, and even if the angles were negative and so r's were negative and so on, is still correct. Well, what if I go ahead and square both of these things and add them up? X squared is r squared cosine square of theta. Y squared is r squared sine square of theta. Adding them up, x squared plus y squared is r squared times cosine square plus sine square. And you remember from your trigonometry that sine plus cosine square is 1. Well, we could tell that right away from Pythagorean theorem, x squared plus y squared, 2 legs squared is equal to hypotenuse squared. So that is, so let's write it the other way, like I have r on this side and x and y on the other side. This is format traditionally, you have a x and y, and you're translating your quantities to polar, and so you get your r from here. How about r? Well, it all depends. if you allow positive or you also, excuse me, if you allow negative numbers or not. So R is one of these two numbers. Sometimes people stay with the positive numbers just to simplify things. You have to look at the problem itself to see if a negative R is allowed or not. How about figuring out theta in terms of y and x? Well, simple relationship is to take the ratio of these two. If I divide sine by cosine, what do I get? Sine by cosine is tangent. So tangent of theta is a ratio opposite by adjacent, or just y divided by x. Sorry. So now we have this transformation formula, and this is the other one. So the first one is going to translate from polar to Cartesian, and here from Cartesian to polar. This one straightforward to apply. This one, we said with R you have the issue of, well, plus or minus, which one of them do you have in mind? And with tangent, there is also an issue that if you have an x and a y that gives you this angle, you have also a lot of other angles that have the same tangent. That is, if I come to the other side here, so not only the original theta has that tangent, if I come to the third quadrant, continue that line, that also has the same, so not only theta is a solution of that, but theta plus pi is the same tangent. And if I go around the circle and come back here, of course, I have theta plus 2 pi and theta plus, if I continue and come here to 3 pi and so on. So in all, it becomes any multiple of pi can be added to this, and tangent will be the same. So with getting R, we have two possibilities, and with theta, we have infinitely many possibilities, depending on how many times you want to go around the circle. So again, things to keep in mind when some puzzling things do come up. Next issue is, well, what are we going to do with this new toy that we have? We have polar grids and polar coordinates. What do we do with them? Well, of course, what did we do with x and y's? We studied curves. Curves were geometrical shapes. We translated that geometry into algebra. For example, we had y equal to, sorry, so we in algebra, pre-calculus, calculus, and so on, you have these shapes, and you come up with the formulas for the shapes. For example, for a parabola, you remember y equal to x squared. So we have a relationship between x and y translating to some kind of a shape, hopefully a recognizable shape. If I give you a very simple equation like y equal to 1, now what would be that curve that corresponds to this? Well, y equal to 1 is a horizontal line that is at distance 1. But if I ask you to graph x equal to 2, well, x equal to 2 is a vertical line that, those are extremely simple curves. Well, let's do the same thing with polar coordinates. Let's start with the simplest. Suppose I ask you to graph r equal to 2. Well, r equal to 2, we said, set up points whose distance from the origin is 2. So I say 1 and 2. All of these points have the property that r is equal to 2. If I had asked r equal to minus 2, would have been the same thing. So this circle is somehow corresponding to some of the lines that we were drawing here. Well, if I had asked you to graph theta is equal to pi third, what would that mean? So pi third, we go 60 degrees, we get to some point. These are all points whose theta will be pi third. On this side will be the ones that whose r is positive, on the other side are the ones whose r is negative. So this becomes a line. So r equal to some number is a circle, a theta equivalent number is a ray. And notice something interesting. These ray and circle intersect at 90 degrees, exactly the same way that these two were intersecting at 90 degrees. So when we go look at these grids, we see this interesting property that the grid lines, well, we had grid lines here. The grid lines now are circles and rays, and they are, sorry, they are always perpendicular to each other. You notice that this is always perpendicular. Okay. Okay, now let's go after some polar curves that are going to be more interesting than just these circles and the rays we had here. Let's go after some interesting examples of, so let's call this thing section. Well, these are polar curves, which are just the equivalent of x and y axis that we had over there. How about some other polar curves? Here is an example. Suppose we want to graph, excuse me, r is equal to, say, 3 cosine of theta. So here's the problem. Plot this polar curve. So the assumption is that r and theta are representing polar coordinates. We want to graph this. What do we do? What would we do? Well, exact same thing that you did back in algebra 1 in high school. You make a table, you find your points, you plot each point, and try to guess what kind of a curve you're dealing with. So here, what we do is to make a table. So given a theta, we are finding r for ourselves from here. Let's go ahead, write some angles. So when you were graphing parabolas, you were going through points like 0, 1, 2, 3, and so on. Here, the traditional choice for theta will be the ones that you're familiar from your trigonometry class. So what are the familiar angles? So I have like 0, perhaps I remember what is cosine of pi third. Maybe I put that now in pi half, and so on. Let's just keep it at that. Maybe put the pi here as well. What is cosine of 0? Well, that is 1 times 3. That would be 3. What is cosine of pi third? That is 1/2 times 3 is going to be 3/2. Cosine of pi half, that is 0. So you might have a table of your trig values so that you can do this thing quickly. So I have 0. Let's pause for a moment and see what do we have so far. So I go ahead, set up my page. My page has the x and y axis because this is my polar axis. And y-axis tells me where I go toward the positive angles. So when the angle is 0 means I'm here. I'm supposed to go 3 units out. So I go 3 units out. This is a point with the coordinates 3. That's my r, and angle is 0. accidentally. It's the same with the Cartesian. Pi third. So it's good to have a polar grid available to us. So pi third is going to be perhaps somewhere along this line. So this is pi third. On this one, I want to go 3/2. 3/2, so the radius that I will have is going to be 3/2. So I'll be somewhere around here. That is, so by now I have my r is 3/2. My angle is pi third. By the time I come to pi over 2, which means I'm taking this axis and rotating it until I hit the vertical, by that time my r has become 0. So you notice this peculiar situation that the coordinate points to the origin. The, the, the numbers that brought us to this point were pi over 2, excuse me, 0. Sorry, we write the r first, so I made a mistake. R is 0. The angle is pi over 2. So it looks like somehow from here we came up, we came to this point and came to this destination. What if I go to angle pi? Angle pi means I have opened my axis in this direction. So by now my angle is pi. At pi, cosine becomes -1. -1 times 3 becomes -3. So we are back in this point, but now my r is -3 and my angle is pi. So somehow from this point we came up to here, we came to this location, and then we went through angles between pi over 2 and pi. And if you fill in the details here, for example, like what? So suppose I have 2 pi third. So 2 pi third will be something like this is the angle 2 pi third. What's the cosine of 2 pi third? That's -1/2 times 3 is going to be -3/2. So I have, so this is the angle 2 pi third. On this axis I have to go down by -3/2, so it becomes symmetrically positioned with respect to that. So it becomes -3/2, and the angle is 2 pi third. Well, what does this look like? Let's just make a educated guess. I'm coming up, I'm going through this point, making it through the origin, come down here, go through this point, and come back to this point. I'm completing the circle, but interestingly enough, I'm completing it in an angle of pi. By the time I hit pi, I'm back instead of 2 pi. So I went up, I came down here, came back here, and that's the plot. Well, we said it's a circle. How do I know it's a circle? Could be somebody else. I have to actually establish that, show that this is a circle. So that's an additional problem. Show the curve is a circle. Well, how do you know something is a circle? Find center and radius of the circles. How do we do this thing? Well, these transformation formulas are the one that are going to be crucial. So I have r is equal to 3 cosine theta. I can approach this problem in a variety of ways. In our transformation formula, you see that when I want to go to Cartesian, r cosine, I have a ready-made thing for it, and same way with r sine. So If I have r cosine, I say, okay, let's lend an r to this so that I'll have r cosine, but well, I have to treat the two sides the same way. I have to treat the both sides the same way, and so I'll have now r squared is equal to 3r cosine theta. So why did we do this thing? Because transformation formulas that we have are easier this way. R cosine I know is x, and r squared I know it's x squared plus y squared. So x squared plus y is equal to 3x. Well, now we are back in algebra 1. We wanted to show this is a circle. Well, this looks like equation of a circle. Well, how do you find the center and the radius? Very simple. You bring x squared minus 3x to this side, and then y squared here now is equal to 0. You remember you do the completion of square. Divide this thing by 2 and square, so minus 3. You divide it by 2, you square it, add what does this do? What it does is that it allows you to use the squaring identity. This, by this approach, becomes a complete square, and you have another complete square, and this is 9/4. So this is a trick that you learn in algebra 1, completion of squares, which is kind of with you all the way through to all the math classes you take. Somehow this idea is present everywhere. Well, now what is center? Center are the numbers subtracted from x and y. 3/2, nothing subtracted. So let's remind ourselves what was the general equation of a circle. X minus h squared plus y minus k squared is equal to r squared. It had center h and k, and the radius is r. So what is subtracted from y? Well, nothing. And the radius is the square root of this thing, which becomes, for a circle, we just report radius as positive. Center and radius, which is exactly what this thing is. This is the center of this thing, 3/2, and the radius of it is another 3/2. It passes through the origin at the angle of pi over 2, and that completes the picture for us. So we made sure it's a circle, and we found the radius and center of it. We noted that we make through the circle one round of circle in angle pi, not 2 pi. Okay, so that was an example with a curve that we were familiar with. Of course, when it comes to polar coordinates, a lot of equations that we write have graphs that are somewhat new to us. Perhaps you might remember them from pre-calculus, because there you have the same topic of polar coordinates, but maybe it has been a while since you took that class, or perhaps in that class you did not spend that much time on graphing. So let's take another picture here. Suppose I ask you to graph r is equal to 2 plus cosine theta. A number plus another number times sine or cosine theta. These are some of the basic topics that come up here. R is equal to a plus b cosine theta, or r is equal to a plus b sine theta, are some of the famous curves that show up when we are doing polar coordinates. If you allow me, I'll change my mind here and start with a 1. The resulting graph is a little bit more classic than the other one, but they all fall in the same family of curve referred to as limosons. So we said we are going to make a table. Theta and r is equal to 1 plus cosine of theta. Again, we go after some of the familiar angles where r would be rather easy to calculate, so I'll go after pi third, pi half, perhaps I come to pi. Let's see what we have so far. At 0, cosine of 0 is 1, plus 1, it becomes 2. Pi third, cosine is going to be a half, and 1 becomes 3 halves. Pi over 2, that's 90 degrees, cosine becomes 0. We are at 1. And then after pi over 2, this becomes negative. So for example, let's write 2 pi third. At 2 pi third, cosine is minus a half, and a 1 that makes a half. At pi, cosine becomes minus 1, plus 1 makes 0, which means we have arrived at the origin. Let's go ahead and graph what we have so far. See, we can guess what else is going to happen. So at angle 0, let's say this is my 1 and say this is 2. I am at this location. At pi third, so the 60 degrees, something like this. I am at a distance of 3 halves, so 3 halves will be somewhere here maybe. So this was location 0 and 2, and this was pi third and 3 halves. At pi half we get to 1, so this is going to be 1. Excuse me, I made the same mistake again, sorry. Let's see. Out of a habit of Cartesian, where the first coordinate is written first, here for whatever reason the textbooks go with r and theta. As opposed to theta and r. So this is going to be 1 and then we have at angle pi, which means, well, maybe we do 2 pi third first, 2 pi third somewhere here. Distance has shrunk to, so 1 half and 2 pi third. We go further at pi, we hit origin here again. So 0 and pi. So what is happening here, we have gone from here to this point and then arriving at the origin. Okay, I can continue with my angles toward pi. I can also adopt a faster strategy. I can take my theta to be negative angles, like minus pi third. Minus pi third, advantage is that the cosine of negative angles, cosine of minus theta is same as cosine of theta. So I am not calculating anything again. It's going to be same 3 halves. That is, if I am at the angle of minus pi third, the distance I go out will be same as what I had over here. So like the point and that point are going to be symmetrically positioned with respect to polar axis. So all of my locations are going to be mirrored below the x-axis. So the picture that we get at the bottom is just a copy of what we had at the top. It's going to be something like this. Well, I didn't do a good job of drawing this thing. It's supposed to be a heart shaped, and for that reason it's called a cardioid. Now, as you change these numbers, the A and B, you are going to get different versions of this thing. The class is referred to as the limicons, and you can see extensive set of pictures for them in your textbook, and I leave that to you so that you can study it there. Another example that would be interesting to look at is when we have a multiple of this angle. Let's go ahead and take a case of cosine of 2 theta. You notice that what happened here is that we don't, before I go to the next one, the shape is not familiar from what we have done before. It's not a common Cartesian function, but what if you wanted to actually see it in Cartesian? What would you do? Just as we had before, so let me, sorry for going back, I go multiply by r, so it becomes r squared is equal to r plus r cosine theta. So as before, r squared is x squared plus y squared. R, well, that's, you remember, is plus or minus x squared plus y squared in the square root. R cosine is x. And that is an unfamiliar equation. We can modify it so that the radical goes away, but unfamiliarity doesn't go away. If I can bring the x to this side, x squared plus y squared minus x, then I have the radical on that side. If you want to make the radical go away, well, you have to pay a price for it, which is to square this. Well, now you have an equation that is written in Cartesian, but notice that you will have x to power of 4 in it and lots of other things. So it's a rather crowded equation with lots of powers in it, and is of degree 4. So it would be unusual that we would have studied such a thing in Cartesian because of the complication of the equation itself. Notice that graphing it in polar was not that bad, while this would be quite a challenge to overcome. So you notice the advantage of going to polar. 1 plus cosine wasn't familiar, but it's not as bad as this one. Okay, now let's go to the next topic. R is equal to cosine of 2 theta. For this type of problems, I suggest you make 2 columns for your angle. If you have a multiple, make 2 columns, and then I'll explain shortly cosine of 2 theta. So you're calculating cosine of this angle. So if I say 2 theta is 0, cosine of that would be 1, so no surprise there. Theta is half of 2 theta, well, that's of course 0. Next angle I'm comfortable with, I don't need a calculator to wrestle with and such. Next angle for which I can calculate cosine of that angle very easily is going to be pi third, because I know cosine of that is half. But if 2 theta is pi third, means my angle was pi 6. Notice that we are not calculating cosine of pi 6 directly, which would have been radical 3 over 2. You could, but we don't have that. So here my angle is pi 6, my cosine is half. what's the next comfortable angle is going to be pi over 2, which happens at the angle of pi over 4, and cosine of that is, of course, is 0. Next angle to look at is 2 pi third. Cosine of that is minus a half. The angle happens at pi third, of course. Going further, at 2 pi, at pi, that happens when our angle is pi over 2 and radius becomes minus 1. Let's go get a handle on what we have so far before we go any further. So again, I draw my XY coordinates. By the way, there are graph papers available, and there are graph papers for polar. If you have access to that, it makes your life a bit easier. So we are graphing theta, and this is r. So angle 0, distance 1. So let me say the 1 is here. So 1 and 0 is at this location. So next, 30 degrees, we have a half. So at 30 degrees, let's say this is 30 degrees, we have come to a half. So 1/2 and pi 6. At angle of pi over 4, we are hitting the origin. So pi over 4 is going to be half of this angle that I have here. Sorry, clean this up. This is the angle pi over 4. So what has happened so far? I have started from here, come up to this location, come down to 0. By the way, one of the interesting things that we are going to see later on, the angle at which we are hitting the origin, that's also the tangent line that passes through this point. So theta equals pi over 4 is the tangent to our picture at that location. Okay, at pi over 3 will be somewhere around here. My r has become negative. So what does that mean? We said negative means go to the other side. So now negative will be somewhere around here. So this became negative of 1/2, which happened at pi third. By the time I hit pi over 2, this is my angle pi over 2, my r is negative. So let me draw it down here. So the angle became pi over 2, r is negative 1, so I am here. So what we did is that we passed through this, we came to this point. Now if you continue through the next 4 quadrants, what you are going to see is that this is going to come back here, go make another petal here, come back here. So let me maybe graph it in different colors. So in the next quadrant, and then in the next quadrant, and in the next quadrant. So I hope you patiently go and draw all of these. And you notice that we have something looking like a flower. And for that reason, it's called a rose. and then they count petals. So it has 4 petals, or they refer to it as 4-leaved rose, and so on. So you want to experiment with sine and cosine with different factors here and see what kind of shapes you get, and classifications of them also in your textbook. Okay, let me keep this short. There is a discussion about symmetry of graphs in polar coordinates. That's a bit extensive and can be also challenging. A brief version of it shows in your textbook. Read that for the next time. Until then, good luck and God bless.